Welcome back. And this is the time I really want to take and cover a few things, and I'll try to make this as a single video. Um, you have to watch this particular video more than once because there are a lot of finite nuances that's contained in the video. If you just casually watch it, get the major points, no, there's also other major points that are hidden, like said in a way that maybe overlooked. So you may have to watch the video just more than once. Don't say I didn't say it, I've said it. All right, it's recorded, so you can't say I didn't say it. So, all right, so here's a problem. This is sort of an extension of that, the square root of thing you found. It's kind of the same deal, but it's much more even easier. So nitrous acid is a weak acid, which we know because it's not one of the acids in the list of 6 strong acids. And the question is, what is the pH of the solution that contains 1 molar KNO2 and 0.5 molar HNO2? The question appears something like this. What this compound really is the conjugate base of this acid. This is acid. I mean, K is a spectator ion, so essentially this is just NO2 minus. So if you write this, though, this is the conjugate base and this is the acid. So if I actually put it here, you'll see that this is the acid. This reacts with water. This is the conjugate base and this is the conjugate acid. So I should have write it here because I've also asked you to identify acid base, conjugate acid base in the above equation, which I already did it for you. All right, is HNO2 a weak acid or a strong acid? I said that at the beginning of the video. It is a weak acid. Now, when you see information like this, okay, this is exactly what we did do in the lab, or for lab number 10, is we created buffers, okay, and tested the pH, okay. So whenever you see a weak acid and its conjugate base, okay, weak acid and its conjugate base, or a weak base and its conjugate acid, this is a criteria for a buffer. That's all there is. And whenever a buffer, well, there's only one equation that's screams loud about buffer, and that's Henderson-Hasselbalch equation. And what is that? Well, there's 2 equations. If the product is acidic, then you have the acidic Henderson-Hasselbalch. So pH equals pKa plus log of conjugate base concentration over acid concentration inside. I'm going to put this 2 inside a giant bracket. Okay. All right, so we are asked to find pH. We are given the conjugate base concentration, which is 1 molar, right? That's NO2 minus. We know the acid concentration, so this is 0.5 molar. And we know Ka, so how do we find pKa? Well, I've given this equation on the back of the appendix for lab 10. pKa is similar to pH, which is negative log of Ka, okay, and pKb is equal to negative log of Kb, okay. In this case, we're only dealing with Ka, so it's negative log of this 4.5 e to the negative 4. So what does that would be? Just don't try to watch the video and try to memorize what's on the screen. That's really poor learning. You don't really get nothing out of it. If you don't understand it, ask me or watch the video again. You would probably understand it the second time. Just don't try to take a photo image of what's on the screen. It's never going to help you. So pKa is 3.34 or 3.35. Okay, so we know pKa. Let's go put everything in this equation to find. Now, you only use this equation or the base version only when you know both the conjugate base and the acid concentrations, okay? All right, so 3.35 plus log of, well, conjugate base is 1 over 0.5, and then take the log. Well, 1 over 0.5 is 2, and log of 2 is 0.30. So 3.35 plus 0.30. So pH is 3.65. And that is it. This is very, very easy. You know, we will probably come back to this again on the homework. So, but like I said, don't try to take photo image of the video and try to remember everything in every video. It's just not going to work. Okay, try to understand, and if there's any component of it you don't understand, then always ask me. I'll be happy to tell you and maybe clarify the mistake that you would probably have. All right, and there's one more thing I want to point out from the Lowry-Bronsted, which is related to the buffer. You see how every single thing in every video is so related, and that's the part that I love the most. Okay. Oops, sorry. So here's the question. I ask you, determine which of the following pairs can result in a buffer. You cannot just take any weak acid under its conjugate base. It has to be, there's a unique factor, and that is when you're given a pair like this one, okay, the difference in the number of hydrogens, okay, difference in number of hydrogens has to be 1. Otherwise, it cannot be a buffer. Why 1? Well, see if you can figure it out, okay? But I don't think that really is the scope. If in a given pair, and I ask you which of the following can result in a buffer, if you take these two, there's 2 hydrogens here and there's 3 hydrogens here. The difference is 1 hydrogen. So this can be a buffer. Here is 3 hydrogens, here is 1. So it's 2 hydrogen difference. No. Here it's 3 hydrogen, here it's 0 hydrogen. So the difference is 3 hydrogens, cannot be a buffer. Here it's 2, here is 1. Sorry, 1. So the difference is 1 hydrogen, can be a buffer. Here it's 1 hydrogen again, 0. So 1 hydrogen, so it can be a buffer. Here it's 3, here it's 4. Don't worry about the negative. 4 minus 3 is still 1, so this can be a buffer. This is 3, this is 2, this is still 1 hydrogen, so this can be a buffer. So the thing is, the difference in the number of hydrogens in the pair has to be 1. And if that is the case, then that combination can act as a buffer. Okay, this is where we tie the buffer back to the Lowry-Bronsted concept and see how everything is so related. And this is what we try to do. I can tell you which ones we did in the lab. We did this. Sorry, we did this. Yeah, I mean to circle this. Yeah, this was one of the pairs we did. This was one of the other pairs we did, and this was one of the pairs we did. These are the 3 pairs that we did in our previous lab. If finding NH2 minus is hard, so we didn't do it. So these are the 3 components we studied in our previous lab number 10. Okay, we created those buffers and then we tested them to the addition of acid or base and how they reacted, and we came to some conclusions. All right, so that concludes every single material on the topic of titrations and buffer. I know I could have done a couple more things, but in lieu of time and other constraints, and then how far you get tested on outside exams, I think I've done my best to cover everything I can. But if time permits, maybe we can learn a couple of things. Okay. All right. So stay tuned for a newer topic called chemical equilibrium. Okay. It's going to be fun. You're not going to get many things wrong in that topic. It's very easy. Trust me. So stay tuned.